a promise in this thread that at the end of the thread I set. When you call promise set value, that unblocks, that gives that the future now has access to that result, and it gets unblocked. So, but you got to call set to make that happen. And so I can't use this future up here. I need to have a copy. And so the way that happens is that okay. The way that happens is my standard thread, here I'm starting the thread, I'm passing it to the lambda, the argument, I'm moving the promise. So this is a move construction, really quick. So there is inside the lambda a new promise that just stole the future, that link to the future, okay? And so now, after I'm done with my work, I can set so this is a new promise holding that now owns that future, because when you move, you're changing ownership, you're giving the ownership to that constructed object, and so this promise owns it, and he'll live as long as that thread lives. He doesn't go out of scope. That's what makes this work. Now, so my thread starts to run. I detach the thread, so you never have to call join or detach. I detach the thread, I return. So what happens is I create the thread, I create the thread, detach it, and return immediately. Bam! Almost immediately do I return. And the thread goes on and does its job. So here, I have a function announce that's one of the callable objects. I'm going to pass it. And here I'm declaring these just to make it simple and quick to write this. So here's standard future of R equals my custom async. I've got to templatize it on the return type because the compiler has trouble inferring that this is really what, that R is the type that I want to return. And I pass it the callable in the argument, and I return from synchronous. And now I'm going to do the same thing. Now here I'm waiting for the result right here in this r.get. I'll block here until that thread returns. And normally, at this point, I would be doing work here before I call that get. And I can repeat with a lambda, so here's my custom async, and I just declare a lambda in the body of it, and away I go. And so if I run it, sure enough, voila. So that's how standard async works, except standard async does one thing that this custom doesn't do. What standard async does is it was written instead of with a template, it was written with a variadic template so I can give it any number of arguments I want. Now, you've seen me use variadic templates. I did that for a join in one of my other demos. I wrote a join all that used a variadic template. Variadic templates won't be on the midterm. But we will talk about variadic templates later in the course. Toward the end, we're going to do template metaprogramming, and if I haven't talked about variadic templates before, then I will then talk about variadic templates because they're often used in template metaprogramming. So variadic templates is basically I can pass in a arbitrary number of arguments, and what it does is it takes the first one and operates on that, and then it returns the rest of the list as it just keeps peeling off the first one and doing the job, peeling off the first one and doing the job. But you got to stop it. You have to have a template that stops that recursion, because this happens at compile time. All that recursion happens at compile time. Okay, is it template? inferencing, type inferencing. So the standard async will let you supply an arbitrary, however many functions, however many arguments your function needs. Standard async is perfectly happy to let you supply because it's implemented with a variadic template. So that's the only real difference. Okay. But this is your mental model of how it works. I got a promise and a future, and I gotta move the promise into the thread function, and then I return the future, and the promise and future act like the future acts like a blocking queue with one element, and the promise is acting like an enqueuer. So when the thread is done, it enqueues this. Here's the result, ready to go. Okay. One other thing I want to quickly talk about thread pools, and then we'll turn to the midterm. So thread pools and tasks. So let me I want to look at thread pools first. So here's threadpool.h. So here's what thread pool does. It's templatized on the number of arguments, the number of threads that I want to spin up. So basically a thread pool is a queue with a whole bunch of threads waiting on stuff to come through the queue. And what's in the queue are work items. What I'm trying to do is keep reusing threads. I don't want to keep creating them. So here's a situation where I've got a continuous set of things coming at me that I want to run on a thread, but I don't want to spin up 10,000 threads. Okay, I'll bring my machine to its knees. So I just spin up some finite number of threads, maybe 8 threads or 16 threads or something like that, based on the number of cores on my machine. I spin up that number of threads, and each thread sits there and waits to pull a work item out of the queue. And you say, but how can I reuse a thread? A thread runs on a single function. I can't change that function. I can't. So what I do is I give the thread a function that executes another function that gets out of the queue. That's all I do. Piece of cake. So here's my standard function. My call object doesn't take any arguments and returns a bool. And the purpose of the bool is just to shut down the thread pool. So when I want to shut down the thread pool, I'll send it a callable object that doesn't do anything but return false. If it's true, it keeps on. It says continue. True is like a continue. Keep going. So and so work item. What the heck does work item do? So I'm going to give it a callable object, and all work item does is enqueue that object. So here's my work item, and what do? I just enqueue it. All this stuff is just a debug statement. So this is the only thing that's of importance. I just enqueue the work item. Okay, now let's look at the constructor, because that's where the interesting stuff happens. So here's the thread pool. Let's peek at the definition. Well, let's actually go to the definition. That's a little hard to see here. So let's just scroll down and look at the constructor. So what does the constructor do? It creates a lambda that, while true, call object co equals q.dq, just pulling a work item out of the queue, and then now it executes it. In this if statement, it executes the callable object. If the callable object returns true, it then just goes back and gets another one. Goes back and gets another one. Goes back and gets another. If the callable object returns false, so not makes it true, then I enqueue it back and I break. Why would I enqueue it back? It's a great midterm question. Why would I enqueue it back? So I put one stop in my queue, one thread, pulled it out, and it's going to stop. But I want to stop all the threads. So that stopping thread enqueues it again, Okay, and the next guy will get it and stop. And the next guy, maybe the third guy, still has 2 active items in his queue. No problem. The stop is behind those 2, so he executes those 2, and then he stops. So it's a really cool way of shutting down the thread pool. Okay, there's a wait function, and all it does is wait on all those, wait on all the threads to stop. So you know, so if I, so let me finish. So here's the function that runs the function. This is the thread function. But what this constructor is, so this is the thread function from here to here. This is what the thread runs. Now, the constructor, okay, starts up a loop, however many threads that I want to start up. It creates a thread using that thread proc, okay, and then it pushes that, the thread, using standard move, it pushes it onto the, there's a vector of threads. This thread pool is holding a vector of threads called threads underscore. Okay, it just pushes it back. And now my wait all is just going to join each one of those threads. Okay, so in my, here's the work item just in queuing stuff. Here's wait. So what does wait do? This is just a little debugging statement. For auto thread in threads, thread.join. Just joined it. Okay. So, and this clear gets rid of that last work item. So that stop item, the first thread got it, the second thread, then finally the last one got it. All the other elements in the queue are gone, but there's that one left item in the queue, and so I remove that with this clear. It's just getting rid of, tidying up that one last little, wouldn't make any difference whether I did that or not, but you know, just being, you know. And the destructor just calls join and joinable. So, okay. Now, I have a task class too. And the task class holds a thread pool as a static member. So task is a wrapper around a static thread pool. And each of its functions don't do anything but delegate to the corresponding function in the thread pool. Task is just a thin wrapper around the thread pool, but it made it static. Why would it do that? Maybe I want to generate 1,000 tasks. If each task had its own thread pool, I've just generated 1,000 thread pools. I don't do that. My whole reason for using tasks and thread pools is to run stuff asynchronously without spinning up a whole bunch of threads. So if I make it static, and I limit the thread pool to 8 threads, no matter how many tasks I generate, I'm always only going to have 8 threads. Okay? So I can use task anywhere I want in my program. Just use task, and I know I'll never generate more than 8 threads or 16 threads or whatever I say in my template argument. Okay? Piece of cake. Suppose that I had I wanted to divide my tasks up into 2 categories, and I wanted this category to share a thread pool and this category to share a thread pool. Maybe, for example, I've got some continuous thing, it's just going to keep pumping, maybe this is a web server and I'm responding to client requests, so I need threads to run each request on. So, but I might have some really important stuff that I wanted to run on high priority thread, or I wanted to give and so I don't want that important stuff to sit and wait in this queue, waiting for a thread pool thread to get around to servicing, because in this high traffic environment, that thread pool may have a lot of items in it. So, so I may want to have a separate thread pool. And so how would I do that? Remember, this is a template class. It's another good midterm question. So this task class is templatized on a number of threads. Suppose I add another argument, int. Thread pool task of 8, 0 is a different class from task of 8, 1. Different arguments instantiated means a different class. Different classes mean different statics. Just because they're both named thread pool doesn't mean that they're not the same class. Thread pool of 1 is not the same thing as thread pool of 0. I'm sorry, task of 1 is not the same thing as task of 0. They're different classes, so they have different statics. So I can categorize the statics, you know. Very often want to do that. You know, for example, I might want to have a thread pool serving incoming messages, and I might have a thread pool serving outgoing messages. So I want to queue up incoming messages, and I want to queue up outgoing messages. And I sure as hell don't want to share the same threads in both of them, okay? Because they're not going to do exactly the same thing, you know? And I don't want to have to sit and look at the, you know, if you're work item, if you're this, go do this, if you're, you know. So that's how you do it. Okay, so let's get to the midterm. One really good way to study for the midterm is to go and look at last year's midterms. It really is. If I were in your shoes, the first thing I would do at the beginning of my study period for the midterm, which would have been last week sometime, okay, would be to look at each one of those, and when I got a question that I couldn't answer, then I would go study that material. That's how I would decide what to really study. I'd look at each of the questions. If I can't answer it, go study that material. Can't answer it? That's a great way to prepare for an exam. That's the way I prepared for my doctoral qualifying exams, and it worked like a charm. I got up and walked out of those exams when they were half over, because that's exactly what I did. I had a collection of material, you know, and what I did was I didn't study anything. I just looked at that material. I had back exams from courses, you know, from faculty. I knew they were going to make up questions for the qualifying, you know, that sort of stuff. But anyway, so you know, looking at these is the best thing you could do to prepare for the midterm. Provided that when you get a question you can't answer, you're honest with yourself. I can't answer. I don't know fully how to answer this. Then you go study that material. You look at my solution, but don't stop there. Then you go look at that material carefully. Okay. You'll need to know the difference between syntax and semantics. In questions, I will sometimes say, describe the syntax of, or describe the semantics of. And if I say, describe the semantics of, you don't need to write any code. If I say, describe the syntax of, you don't have to describe the meaning. Okay. And I'll say that, and I'll have people do both, and you know, spend a lot of time. Questions that ask you to produce or analyze C++ code. You absolutely will have at least 2 questions that ask you to write code. One of them will be a threading question. Every exam has a threading question. A question that requires you to write threading code. Every exam has a question that asks you to write code that isn't threading code. You're allowed to bring in a sheet of notes. 1 page, 8.5 by 11. somebody asked if they could bring in a dustpan size. And I said, sure, you can bring it in. I'll tear off an 8.5 section of my choosing. I'll choose which area to tear off. So, and it is pointless to write code in those notes. You know, to write down this whole example, you know, blah, 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 blah. Because the chances of me asking that question are about the same as the chances of you being struck by lightning while you're sitting here taking the exam. Okay? Ain't going to happen, guys. And so I see people, you know, they don't know how to answer the questions. Copy, 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 you know. Because to put something down on the paper, oh, he won't read it. I do. I read every single line. And so if you do that, you'll get a 0.0 or 0.1. If instead you said, I don't know how to answer this question, but here's what I know about it, you might get a 0.5, 0.6. Okay? Another thing you probably want to do is when you sit down, you should, there's going to be 7 questions. You should look over the questions and decide, these are easy. I know how, I can answer. I'm not sure about that one. So then take all the ones that you can answer quickly and answer. And for the code questions, it would make sense for you to write some pseudocode. Just not a lot, just you know, anything pseudocode you can write in 1 minute. Because if you run out of time and you don't get back to that question, you won't get a 0. I have given 0.85 for when I asked you to write code. If the student had written really accurate pseudocode that really describes what's got to happen, they might get 0.85 out of that. I won't guarantee you if you write pseudocode you're going to get 0.85. You know, it's got to be really accurate. But you know, that's a guard against running out of time and then, you know, having these questions that get 0 points. And, you know, it's a good idea to answer all the questions that are easy. Answer them quickly, you know. There's no point in writing and writing and writing and writing and writing. I see people sitting at the exam, you know, writing on and on and on. I'm groaning inwardly for 2 reasons. One, that student is wasting valuable time that they should be thinking about other questions. And 2, I got to read all that stuff. Okay, I do. I read every single line. And there are times when, if it's disorganized and barely comprehensible, I may spend a lot of time trying to figure if there's any value. Is there any value to this answer? Yeah. And when that happens, I'm sitting there gritting my teeth. You know, you don't want me gritting my teeth when I'm grading yours. Now, I won't know. I don't know whose exam I'm grading. I know the first guy. So what I do is I take all the exam 1s, for example, or in your case, all the exam 3s or 4s. I have a stack of them, and I start with the first one. I grade the first problem, grade the first question. So once I'm done with the first question, I no longer know who I'm grading. And I do that intentionally so that no bias, you know. So my grading is not reflected by what I expect of you. It's just based on what I see. So I do look at them very carefully. By the way, there won't be a midterm. I'm sorry, there will be a midterm. There won't be a help session this Friday because I will be home grading your midterms. Okay, no help session this Friday. Okay, there will be questions about this year's projects. You might be asked to draw a package diagram or a class diagram or whatever. You know, that might be a really good thing to, you know, to do before you come in. I don't know that I would waste a whole lot of space on your notes with it, but having drawn it once, you know, then it'll be real quick and easy. You know, it's going to be a package diagram or a class diagram. You know, so. And it'll either be about Project 1, Project 2, or Project 4. Won't be about Project 3 because Project 3 involves sockets, which we haven't talked about at all, and graphical user interfaces, which we haven't talked much about so far. Okay, so you know what they're going to be, so you can get ready for it. Classes, composition, inheritance, initials. So the relationships, 4 relationships: inheritance, composition, aggregation, using, that's it, baby, those four. And you got to know what those four are. You got to know how you use them. You got to know how you write them. Okay? And that's all right here. This diagram is important. You got to understand it. I won't ask you to reproduce it. I will not ask you to reproduce this diagram. I do not ask you to reproduce code that I have written or diagrams that I have drawn. It's never my intent that you memorize stuff that I've said. Absolutely not. When I ask you to write code, is it possible that sometime in the past I have done a demo just like the question? Yeah, if I forgot that I did that demo, then I might have, I try to make the questions totally disjoint from demos I've given before, but I'm not always totally successful. It might, it might happen, but you don't have to, do not have to memorize stuff. You do not. Okay. But the takeaway here is, what do you know about this? What this says is that clearly, in order for D to be constructed, it has to construct, the constructor of D has to invoke the constructor of B, because B is lies in its memory footprint. So there's no way it can initialize itself without calling B's constructor. And similarly, B's constructor has to invoke C's constructor, because C is within B's footprint. Has to. So what happens is the sequence is D is invoked, which as its first act invokes B's constructor, which as its first act invokes C's constructor, then C runs to completion, then B runs to completion, then D runs to completion. So it's start, 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 finish, 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 finish. And we know that when I construct D, that does not construct a client, and the client does not construct, the client may have called new to construct this, but the client's constructor does not automatically call the constructor here. Okay? No guarantee that that happens at all, because it's not in its footprint. So understanding that, having that mental model, is what this diagram is all about. Virtual function pointer tables, you need to know about this, how it works. So, very likely when you walk over the threshold for an interview, you'll get asked that question. That'll be about the third question asked of you. That's the separator. Do we talk to you do we take you to lunch or not? Okay. If you can't answer that question, we put you on the bus. If you can answer that question, we take you to lunch. Dark corners. So you do need to understand, you need to look at that demo. There's just 4 pages, It's possible that those might be things you might want to, make a few short brief notes about on your class notes. But, don't overload across class scopes. Don't overload virtual functions. Don't override, don't overload virtual, don't override non-virtual functions. Always provide a virtual destructor in a class that may serve as a base. So, also, dark corners are about the operations that the compiler will generate, the construction, assignment, and destruction operations, and when it will, when it won't, when you should do something about it, when you should not. Those are all valid questions, all addressed in that presentation. Temporaries, you want to know when temporaries are constructed. A move operation happens on temporaries only unless you specifically, with standard move, recast a non-temporary to a temporary. Okay. Temporaries are typically things that have no name. Okay. But I say typically because I may have a named thing inside a function, and as soon as I return, it's going to be destroyed, and so for return, it's a temporary. That's why I can't return a reference to something I build inside of a function. You need to be comfortable with, what the string class operations were doing, and why they were written that way. Simply not because I'm not going to ask you questions about the string class. I will not do that, okay? But I will ask you to write code, and you need to know how to do those kinds of things. Okay? So you need to know what a move constructor is, what a copy constructor is, what move assignment is, what copy assignment is. Templates, yes. Functions and class templates, yes. Specialization, yes. Template policies and traits, yes. Will all of these things be on every exam? No. Will all of these things be on at least one exam? Yes. Okay. Callable objects, yes. Functors and function pointers, yes. Lambdas, yes. SCL containers and iterators. I will not ask you the details. There's a lot of details associated with a standard template library that we haven't covered yet, and I won't ask. We will cover it, but we haven't covered it yet, and I won't ask. But you have been using vectors and standard unordered maps, standard vectors and standard unordered maps and strings, and you darn well better know how they work, okay? Because you couldn't have written Project 1 and Project 2 effectively without knowing that, okay? So expect to be, have code where you're going to have to know how to do that. C++ 11 constructs, smart pointers, compiler-generated function, callable functions, aliases, range-based for. All of these things you need to know enough to write code effectively, okay? And for the compiler-generated functions, you need to know all the details. When will a void constructor be generated by the compiler? Okay? Only if no constructors are declared in the function, in the class. Only time. You need to know. And, in several places, including, I think I've said all this in the Dark Corners presentation, but in several places I have, you want to know in the notes section, if you go up to the notes section, there's a note on classes, and the classes talk about the rule of threes, and all of that is described in the rule of threes. Principles. Lookup substitution principle, yes. Open and close principle, yes. Dependency inversion principle, yes. Interface segregation principle, yes. Will you be asked all four of those on your exam? No. Will you be asked one of them? Yes. And just knowing the statement, probably not a bad idea to write the statement really briefly in your notes, but just knowing how to state it isn't worth much. If you don't know how to use it, it's worthless knowledge. Worthless. So you not only have to be able to state it, you have to know how to use it. Where is it appropriate? Understand that LSP is quite specific. Has to do with inheritance and polymorphic operations. DIP is, dependency inversion principle, is quite specific. It has to do with using interfaces and object factories. Interface segregation principle is quite specific. It's all about not making big, huge interfaces that clients only use a part of, because that is very likely to cause you to have to change those clients if you change the interface. OCP, unlike the others, is a very broad. It simply says, do your best to modify rather than change. Try not to change, try to modify instead of change. but it's really a try. So very broad. The other three are quite specific. That one's broad. Doesn't mean I won't ask about it, but. Programming to interfaces, widget factory. If you understand the widget factory example, the object factory and how it works in the the interface and how clients get access to the interface, you're good to go. I won't ask a question about cross-casting like I did in the abstract factory example. Okay, that's really good information. You want to know that. You want to make it your own, but I won't ask it on the exam. So my goal here is in this session, I want to prevent you from spending an inordinate amount of time studying things that are irrelevant for the exam. I don't want you to have to do that. But on the other hand, I don't want to be so specific that one of the purposes of having a midterm is to make you go out and review the material we covered, to help you learn it. So I'm not going to be so specific that there's this tiny little set that's all you study, But I don't want you wasting your time either. So interpret my answers with that in mind. When I say, I won't ask you a question that involves the DLL demo. That's, again, you need to know how that works, but won't ask you a question about that. I won't. RTTI, runtime type information. We talked about it very fleetingly. You've seen me use it once or twice. Am I likely to answer it? Ask about that? Exceptions. So I am going to talk, if there's time, before questions run out, I will do the exceptions presentation, but I won't hold you to that on the exam. Understand that I don't know whether we're going to get to that exceptions presentation, and I've already made up the exams. Okay? So I'm not going to hold you. But you do need to understand, when I ask you to write code, if that code could throw an exception, or is likely to throw an exception, you darn well better have a try-catch block. You need to know how to use it, but, just you've seen me use it a bunch of times, that's what you got to do. Cast, you need to know how they work, So static cast, dynamic cast, const cast, reinterpret cast. I will add to that, the standard move is actually a cast, and there's also something called standard forward that's a cast. We haven't talked about that yet. I will talk about it. It won't be on your exam, I promise you. There will not be any question that requires you to know about standard forward and what it does. But you do need to know about standard move and what it does. But at the end of the course, we're going to talk about template meta programming, and I will revisit standard move and standard forward when we do the template meta programming. So, again, those are questions that are fairly likely to be asked in an interview. What won't be on the exam? So the details of I/O streams. But you need to know how to open a file and check to see that the open was successful. Okay, I'm going to ask you to write code. You may have to write that kind of code. But you don't need to know all the witchy little details about streams and the way they work. We will cover that, but we haven't covered it yet, so I won't ask you about those details. Again, technical details of the standard library. You need to know what vectors do, what strings do, what unordered maps do, the way they behave, both their syntax and semantics. But the rest of the stuff, no. Sockets, we haven't talked about sockets yet, so we will. Right after we get back to the midterm, we're going to talk about sockets. So that's all you got to do. Gee, couple of evenings and you're ready, right? Well, maybe more than a couple of evenings. Can't be too much more because the exam is 2 days from now. I guess a couple of evenings is about it. So, but you're there. You're there already. You know, all you got to do is fine-tune what you've already done. So, all right, questions. Questions about the midterm. Yes.
Could you explain some about shallow copy and deep copy?
Yeah. So shallow copy means if I've got a function that holds pointers, if I've got a class that holds pointers to things stored on the heap, if I do a shallow copy with that class, I wind up with 2 pointers pointing to the same object, which is an error in C++ because when the first of those objects goes out of scope, it'll call delete on the object, leaving a dangling pointer with the other one. A deep copy means that when I copy a class that holds those pointers, I don't copy the pointers, I copy what they point to. That's a deep copy. Now, the compiler-generated operations, assignment and construction operations, do member-wise, do base-wise and member-wise construction and assignment. That does not mean they're doing shallow operations. They are not. They're doing whatever the base provides and whatever the member provides, which almost certainly is not shallow. I've heard students say the compiler-generated operations are shallow, and that's incorrect. Okay. If your class holds a pointer to the heap and the compiler-generated operations will, on that pointer, do a shallow copy because that's what it has, just the pointer. But as long as my bases and members have correct assignment and copy and destruction semantics, the compiler-generated operations work just fine. A pointer does not have correct construction, assignment, and destruction semantics. Does not. Okay? Not in the sense that we're talking about. Did that answer your question?
Yes.
Good. Other questions? Other questions? Are we ready to talk about exceptions? We're going to have an exceptional day, folks. Let's do exceptions. Did I tell you there isn't going to be, I think I told you there isn't going to be a help session this Friday? There isn't going to be a help session this Friday because I'm going to be home grading your midterms this Friday. You don't need it. You've turned in project 2, you've done the midterm, you're getting ready to go to Miami. You know, you don't need a help session. Okay, let's talk about exceptions. We're going to have an exception. I want the PowerPoint. So let's have an exceptional day. So how do you deal with exceptional states? You can do nothing, which is okay for demos. A lot of times I have demo code that literally can't throw exceptions and I don't catch them because it's a demo. Okay? I'm not obligated to do that in a demo. I don't want to do it in a demo, usually, unless my demo is about exceptions, because they get in the way. My demo is trying to illustrate one specific point, and if I decorated it with exceptions and all, you know, any possible, pretty soon the message gets buried in the traffic. So, but demos, that's the appropriate thing, but otherwise it's not. I could just abort processing, but if you're writing flight navigation code for the Boeing 747, you probably don't want to abort processing, right? I could return error codes, and occasionally that's useful. Sometimes I do it, but understand that when you return error codes, the compiler generates a lot of spends a lot of CPU cycles looking for a very rare event. And it means your code is littered with tests for that very rare event. and it means your code is harder to maintain. Okay? So for all those reasons, you might choose not to use error codes. What's left are exceptions. Now, there is one reason for using error codes over exceptions, and that is that when an exception is thrown, code that you plan to execute doesn't execute, and state that you've created has been destroyed. Meaning, somehow, you've got to restore that state and go and execute those statements that weren't executed, probably. Okay? And that can be hard to do. So we'll come back to that question in a few minutes. But generally, exceptions are, of all the things you could do, exceptions typically are the most effective. But, you know, with that caveat. Okay, exceptions use three keywords: throw, try, and catch. Normally in code, you don't see throw as often. Throws happen in library code, but occasionally there's some condition that your code believes is an error, and so you'll throw an exception. Try allows you to construct a region in which you are preparing to handle exceptions, and the catch are clauses that handle the exception. So try and catch, and the try block typically must have at least one and may have a whole chain of catch clauses. So what happens here is if an exception is thrown inside this scope, and understand that the scope is probably a lot more than just 3 lines of code. The scope may call functions, which call functions, there could be an enormous amount of code inside that scope, just hidden from you by function calls. So if I have an exception thrown in this try block, all the code up to and including where the exception happened are executed, but none of the code after the exception is thrown is executed. And as well, every object that was created from the beginning of the scope until where the exception is thrown are destroyed. Their destructors are called. Language guarantees that. And that's so that there aren't resource leaks, aren't memory leaks, aren't resource leaks. Catch clause handles the exception, and you want to catch by reference. We'll talk a little more about that later on. So exception handlers are often arranged in a chain. Try, catch T1, catch T2. And what happens is when an exception is thrown, that exception is tested against T1. Does that exception match T1? If it doesn't, it moves down to this. If it doesn't match, it keeps moving down. And if it doesn't match any of the clauses in your associated with the try block, it'll move up to the next enclosing scope if there is one. If there isn't another enclosing scope, it's an uncaught exception, and that has meaning. Matching attempts are based on the order of the declaration of handlers, so you want to make the most specific first and the most general last. If you make the most general first, you'll never get to any of the others, okay? And typically, you can do more refined stuff with the more specific clauses. Okay, so C++ exception handling guarantees that when an exception leaves a scope, all of the objects in that scope that have been successfully constructed will have their destructors called. There's one exception to that statement. And that exception to that statement is? The exception. If I'm going to create an exception to throw, if I destroy it, okay, won't do me any good. Okay, so all the non-exception objects all of the objects except the one you throw. That's the right way to say it. Because I could create other exception objects and they would be destroyed too, as long as it wasn't the one that I was throwing. Only destructors are called, so resources that are allocated in that scope but not deallocated will be lost unless you're holding onto them with a smart pointer that automatically releases those resources. That's what smart pointers are all about. So if you just knew something, you know, and you don't attach it to a smart pointer, chances are you're going to have a resource leak sooner or later. So in an exception environment, you must make all allocations within objects and deallocate in their destructors. When are you in an exception environment? Anytime you call any library code, any code written by someone else, any code in a function written by yourself, the answer is virtually always. Virtually always, okay? Doesn't mean you're going to write exception scopes everywhere, but you really want a very high coverage of exception scopes. I mean, for example, if I wrote an exception handler in main, everything inside that, you know, everything inside it, so virtually I have a try scope that covers my whole. So your goal is to have very high coverage of try scopes. But typically you'll nest them because at lower level you know more and you can do more about it. When you get up into main, probably the only thing you can do is use an ellipsis catch clause, which I'll talk about in a minute, which doesn't know anything. All you can say is something bad happened. But the good thing is that you won't have the uncaught exception that will do nasty things, which we'll describe in a couple of minutes. If a second exception is thrown while a first has not yet been handled, the special function terminate is called. So what does this tell you about where you should never, ever, ever throw an exception? Great midterm question. Suppose I throw an exception in a destructor. Guaranteed, I'm going to have two exceptions. So an exception happened, so my destructor were called. A second exception is handled before the first is created, before the first one is handled. Set terminate, which by default points to abort. Just hard crash, bang, gone. Matching. So this just talks a little bit about matching. What it says, you know, I can throw a literal string if I wanted to. Big Trouble in River City. That I can throw that. That works. But usually we'll throw instances of a standard exception, and there's a whole hierarchy of them. I'll show that to you in just a minute. But you want to catch by reference, not by value. Because if I catch a derived class by value, it's sliced to the base part. I have a base, copy constructor called, and it just knows how to copy the base part. So I've lost all the derived stuff, and so that means that's what's called slicing. I've rendered my derived object into a base object. But if I pass by reference, I just have a base class reference bound to a derived class object, and all the polymorphic stuff works just fine. All that derived stuff works just fine. So throw by value, catch by reference is the standard litany. Always do that. A catch handler with an ellipse, catch ... that's what an ellipse is, will catch any exception thrown in its context not caught earlier. So this will avoid an uncaught exception. Uncaught exceptions. So if none of the catch handlers for a try block matches a thrown exception, the exception moves to the next enclosing try block. If there's no match in any enclosing try block, the exception is uncaught. An uncaught exception also occurs if a new exception is thrown before an existing one is handled. Cleanups may fail to occur with that uncaught exception. If an exception is uncaught, the special function terminate is called. Uncaught exceptions can always be avoided by enclosing the contents of main in a try block with an ellipsis handler. If I were writing code to submit, I would do that. That avoids 5 points off the top, because that's what happens if you have an uncaught exception. Okay, terminate function. So you can define your, so terminate is a function pointer with default value, the C library function abort. Just immediately shut down. Kill the process. You can define your own terminate handler using set terminate, which expects a function that returns nothing and takes no arguments. It's got to be a global function. So here, example, Arnold, I'll be back. Set terminate Arnold. Okay? Nobody's smiling. That's a joke. Terminator movies, haven't any of you watched the Terminator movies? Arnold Schwarzenegger is the guy, is the Terminator. So Arnold, I'll be back. He always says at the end, I'll be back. You guys are culturally deprived. You are. You don't watch enough late night movies. Actually, it's a good thing you don't. All right. So I like bad jokes. Yeah, you know by now, I love bad jokes. So, and I tell them over and over and over again. All right. Rethrowing. So I may rethrow exception. So why would I rethrow an exception? So this will rethrow E, but I could rethrow a different exception if I wanted to here. And the reason is that somewhere fairly low in my try-catch, set of enclosing scopes, I may catch an exception that I have some detailed low-level knowledge about, but I don't know enough to handle it. So the guy above me doesn't have that detailed knowledge that I have, so I have to encode that knowledge in the exception and then rethrow it so that up at a higher level where he knows how to handle this, what to do in this situation, he has my detailed knowledge, but he also can handle the situation that I don't have enough knowledge to handle. So that's not a common occurrence, but not uncommon either. Okay. Standard exceptions is a standard exception class, and the hierarchy looks like this. There's a lot of them. And notice that the base class has a what function that's not pure virtual, but it is virtual. It returns a literal string. And so in my exception constructor, I can supply a string, and what generates that string that I've supplied. If I don't supply one, then I get a message from the operating system. Basically, the library grabs the last error that happened. Most platforms indicate the last error that occurred, and they just grab that and stuff it out the exception. So if a socket fails, I'll find out that it was a socket failure or something like that. And often, I don't need a message, just the type of error that happened. For example, I think I used range error in the string class when I was indexing. If the index was out of range, was outside the less than 0 or higher than n, less than or equal to or higher than n, I threw a range error. So you can tell from the type what happened. I had an outer range index. Exception specifications were standardized in 98 and removed in 11. And basically what an exception says, this statement says that the function f will only throw E1 or an exception of type E1 or type E2 or type E3. And that's good, except that if it calls any library code at all, it has no idea what exceptions are thrown. And what happens is, if it throws an exception that isn't one of these, then that's an unhandled, I'm sorry, that acts like an unhandled exception, called set terminate. Now, I think it calls unexpected. It calls a function unexpected, which does the same kind of thing. By default, it calls abort. This throw, this has been changed in C++ 11 to no except, which is a interface that guarantees that no exceptions are going to be thrown. That's very hard to do except for very special, I won't say exceptional, very special cases, okay? A pointer swap isn't going to throw an exception. And it turns out that's important. So it turns out that no exception interface guarantee, it's impossible to have a strong exception safety guarantee unless you have this. We'll talk about that in just a minute. This says function f can throw anything. Because of the problems that happened here, these were taken out of the language. The code will still compile, but it's deprecated. You know, they don't want you to use it. Don't use it. Because it was a solution that sounded good that caused more problems than it solved. So specification violation. So we have a function unexpected is called when an exception, when the specification is violated, then instead of calling terminate, it calls unexpected because this is a violation of the exception, and I can set that special function. What happens? So let's go back and think of the unhandled exception, the set terminate. So I'm writing code for my process, and I call set terminate to do what I want, some processing that I want to happen. Maybe I'll log something before I quit. And Naga is writing code for the same process, and he uses set terminate, and he defines it a different way. What do you think happens when an unhandled exception occurs? Only one gets called. The one that gets called is the set terminate that was called last in time. First one just took the pointer, and instead of having it point at abort, it pointed to my function. Let's suppose mine was executed first. Nog's was executed second, and it just took that pointer that was pointing to me and makes it point it to his function. They're not queued, unfortunately. So what that means is they aren't very useful unless you're the only one writing code for that process. Okay, exception safety, basic guarantee. In the presence of exceptions thrown by called global functions, object messages, template parameters, or local calls, the code will not leak resources, will remain in a consistent but perhaps unpredictable state. And that's fairly easy to guarantee. What it says is that I'm using exception handling where it ought to be used. I don't have it says I don't have uncaught exceptions, is what it says. Now, and you say, okay, great. The issue here is that when an exception is thrown, there are statements that my code intended to be executed that aren't going to be executed, anything in that try-catch scope after the exception occurred. And also, the state that I very carefully built is gone. It's destroyed when the exception was thrown. So somehow, I have to recreate that state and re-execute those messages. Oh, that's not easy to do. Not easy to do. So I'm writing flight navigation code for the Boeing 797. Exception occurs. What do I do? I know that, I got a whole lot of state. Aileron position, rudder position, flaps, engine thrust, altitude, airflow, tons of stuff that are important for flight navigation. All gone, bam. So what would you do? I would probably freeze everything while my system quickly went around scanning all the sensors, and then restart. Rather than have the flaps all go immediately wham, down or something, okay, and putting you into a nosedive or something. But it's not easy. What that means is that for correct error handling, I really have to plan that as part of my design. It's not something that you can reliably tack on after the, oh, my design is all done. All I got to do is do error handling. You're going to tear everything apart to get that to work properly. Everything. Shred, 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 shred. Tears running down your face, okay? So it really has to be part of your design. Sometimes it's easy, but sometimes it's not easy. For no SQL database, it's going to be a piece of cake. Not hard at all. Okay. But for a flight navigation system, might be. But the case in point that it might not be that hard. But a lot of cases, if I were writing code for the control system for a nuclear reactor, so the control systems drive rods, moderating rods in and out of the fissionable material. They're called moderators because they reduce the flux, the neutron flux. As they go in, the flux gets lower. And so, you might just jam them all fully in, okay, and shut everything down. Well, maybe you wouldn't want to do that because that'll probably cost the power company $4,368 because it just shut down the entire nuclear reactor and it takes 4 days to start it back up again. Okay, so, but a lot of times it may not be so hard to do, but you need to assess it. In some cases, it's just really tough. Now, there's a stronger guarantee. Strong guarantee. If an operation terminates because of an exception, program state will remain unchanged. That means you have rollback and commit semantics. This is a transaction. Everything you do is a transaction. So you do the work off to the side, and once the work is completed and no exception is thrown, you swap. You do a pointer swap. That's why the no throw is important, because to guarantee exception safety, you have to know that what I'm going to do to get this state replace my previous state is that I do it with no throw operations. Has to be with no throw operations. It's the only way I can make that strong guarantee. But that's wild. Imagine writing the NoSQL database to implement the strong guarantee. Okay. Be a real pain. And it's complicated code, hard to debug, hard to reason about accurately, hard to maintain. If you're writing code for a nuclear reactor, you're going to want to make the strong exception guarantee. If you're writing code for the Boeing 797 flight navigation system, probably want to make the strong exception guarantee. Okay. And almost certainly, you know, what you would guarantee is not that, so what you would probably have is almost a strong guarantee. You wouldn't guarantee that the state is unchanged. You'd guarantee that the state is at least some fairly recent state, like an accurate snapshot of some recent state. Anyway, that's exceptions. So, you know, I just said all these words, so. So we had an exceptional morning. Fantastic. So, midterm, 9:30. Don't be late because the exam will start without you if you are. When you come in, you're going to be asked to leave this first row blank. And then starting with the second row, fill every seat, no empty seats, no bags on seats, a human being in every single seat. I won't pass out the exam until that's true. I use this for people who walk in late. Why people come late to an exam is totally beyond me, because you don't get to go late. You get to turn in yours just when everybody else does. So, but we say that first row for people who come in late. Okay, any questions before we break? Fantastic, you guys are all ready for the midterm. That is good news. And for all of you who are smiling when I say that, I know it's good news. All of you are looking glum. I figure it's probably not good news. I don't have them yet. They haven't given them to me yet. I can't upload anything until they give them to me. I will send them CIT an email, sometime in the next half hour, asking them please to, but I don't know when they're going to be available. They might not be before the exam. I hope that's not true. They come, onto a college server, and they come in pieces, and those pieces have to be assembled to the processing software. So CIT, they don't do it manually. I mean, there's a script, but they got to run the script, and it takes a while. And then they get it. Nothing's there yet. So I'll upload it as soon as I have them. I'll upload it. How can you get a creative project one?
就打了一点点螺丝，过去4年打螺丝，还打了又打又打。我从哪儿？有点厉害。
厉害不好，我早就都跑了。
又没来。现在我压烂了。
大家可能是要。
一个。那个问题在我的手里。
So you're planning to come to my office to talk to me this afternoon? There'll be a bunch of people who want to pick up their grade project ones. I'll do them first. But then there'll be plenty of time. Did Tom ever come and talk to you about like stuff? Oh, okay.
我下午
在家可以